In this module, Module 7, we're going to talk about how to prove that the theorems that we've introduced in prior modules, how we can prove that they're true. So I'll start by reviewing those Boolean theorems that we've already talked about, and then show two methods for proving that these Boolean theorems are true. The first method is called perfect induction, and the second method is to use other theorems and axioms to simplify the theorems and show that the two sides of the theorem are equivalent. So let's briefly review the Boolean theorems of one variable. We have identity, null element, idempotency, involution, and complements. Again, we have the true form and the dual forms of these theorems. We also have theorems of several variables: commutativity, associativity, and distributivity. Again, those are similar to regular algebra or traditional algebra that you've used in prior classes. Again, the exception is the dual form of distributivity, where the OR operation can distribute over AND. Where in traditional algebra, the addition operation cannot distribute over multiplication. But in Boolean algebra, that is a valid operation. Okay, so the first three are similar to traditional algebra: commutativity, associativity, and distributivity, except for the dual form of distributivity. And then we have the other theorems covering, combining, consensus, and DeMorgan's theorem. And for now, these first two of those, covering and combining, are going to be the most important theorems that I want you to understand. We'll use DeMorgan's theorem in later modules, and consensus can be used. Covering, combining are really the most significant bit. I want you to understand those to start with. Okay, so commutativity, associativity, distributivity, definitely understand those. Those should be pretty easy given that you've used those before in traditional algebra. Covering and combining are the other two I want you to focus on for now. We'll talk about consensus a little bit as well, and in later modules we'll talk about DeMorgan's theorem. So how do we prove that these theorems are true? Well, as I mentioned in the introduction, we can use two methods. The first method is called perfect induction. We've actually used this already. And the second method is to use other theorems and axioms to simplify the expressions of the equation and make one side of the equation look like the other. So we can show that, yep, in fact, they are identical. The first method we're going to use is called proof by perfect induction. This is also called proof by exhaustion. We're basically going to check every possible input value. So remember, we're using binary signals or binary variables. So their value, the value of a signal is either 1 or 0. So it's pretty easy to exhaustively check every possibility and see if the expressions are equivalent. So if the two expressions produce the same value for every possible input combination, the expressions are equal. So here's an example of proof by perfect induction or proof by exhaustion for commutativity. B and C is the same as C and B. So we put all of the possible combinations of B and C. So truth table, 0, 0, 0, 1, 1, 0, 1, 1. We have two input variables. The total possibility of combinations is 2 to the 2. If we had three input variables, B, C, and D, for example, we'd have 2 to the 3 rows, or 8 rows. Let's do B and C. Well, we get 0 and 0. Yep, in fact, 0, 0, and 1. 0, 1, and 0. 0, 1, and 1, 1. Okay, so for B and C, we got that result, 0, 0, 0, 1. Now let's try the commutativity, the commuted version of B and C, where these variables commuted or moved across the AND operation. So we get C and B, 0 and 0. We get 0. We get C and B, 1 and 0, still 0. 0 and 1, C and B, again 0. And C and B, 1 and 1, we get 1. So our proof by perfect induction showed that, in fact, these are equivalent. If I do B and C or C and B, I get the same result. So in fact, those two expressions are equivalent because the expressions are the same for every possible combination of B and C. And here, typed out nicely for both possibilities. So we can do the same thing for associativity. Here we have 3 variables, B, C, and D. So now we need, well, for 3 variables, we need 2 to the 3 rows in our truth table. And so we'll have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And again, I put that line there just to keep it aligned. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Those are all of the possible combinations of B, C, and D. And we can do the first expression here, this expression on the left. First, we're going to perform B and C. So for this top 4 rows, for these top 4 rows, B is 0, so we're going to get 0 and something. So we know B and C, that expression, is going to be 0 for those top 4 rows. B and C on the bottom, well, now B is 1, so we're going to get 1 and something. So now we're just going to look at the value of C, because 1 and anything is just that anything. So in this case, 1 and C. So we'll put whatever C is here, 0, 0, 1, 1. And we're going to take that result, B and C, and it with D. So now we're going to get B and C, which we have in this column, and it with D, which is here. And we're going to get, well, we're going to get zeros for all of these rows to start with. So 0, 0, 0, 0, 0, 0, because that expression B and C is 0. And now we get 1s here. B and C is 1, so we're just going to get whatever D is. So B and C and D is going to be 0 here and 1 there. And now we can evaluate, again, proof by exhaustion, evaluate the right side of the expression and see if it is equivalent to what we just evaluated for the left side of the expression. So we're going to start with C and D as the first part. So now we'll AND these two variables, C and D. We're going to get 0, 0, 0, 1. So 0 and 0 gives us 0, 0 and 1, 0, 1 and 0, 0, and 1 and 1 gives us 1. And then we're going to do the same thing for the bottom 4 rows. We're going to get 0, 0, 0, 1 again. And now we can AND these values, C and D, with B. We get B and C and D. So here's our B column. We're going to AND it with C and D that we just evaluated. B is 0. These top 4 rows, we're going to get 0 and something. Look at this, 0. And B is 1 in the bottom 4 rows. So we'll just get whatever C and D is. So 1 and something is just the something. So we're going to get 0, 0, 0, 1. So as expected, but we've proved it here, if we do B and C and then AND it with D, that's the same as if we first perform C and D and AND that result with B. So associativity works. We can also use proof by exhaustion to show that the distributivity theorem is true or valid. So here we have B and C or D. I want to show that that's equal to B and C or B and D. So So that AND operation, again, distributes across the OR, B and C, or B and D. So the first thing we do is set up our truth table. We have variables B, C, and D. So we're going to have 8 rows in our truth table. And now we want to show this left-hand side. So first we're going to show what C or D is equal to. So we look at these 2 columns and OR them together. We're going to get 0, 1, 1, 1, 0, 1, 1, 1. And now we AND that column with the B column. B is 0 in these cases, so 0 and anything will be 0. B is 1 in those 4 rows, so 1 and anything is just anything. So we'll just duplicate that column. Now we want to show the right-hand side of this equation. So we'll put a column for B and C, and a column for B and D, and then we'll OR those together. So B and C, we'll look at those 2 columns. We're going to get zeros, those top 4 rows, because B is 0 in the top 4 rows. And B and C, well, B is 1 there, so that will just be the C column for those bottom 4 rows. Okay, and now we look at B and D. We're going to AND these 2 columns together. Again, B is 0 for these top 4 rows, so we'll get 0 for those rows. And B and D, B is 1 in those bottom 4 rows, and so we'll just get whatever the D column is for those bottom 4 rows. Okay, and finally, we OR those together, B and C or B and D. So we OR those 2 columns together. We're going to get 0, 0, 0, 0, 0, 1, 1, 1. And we can see that, in fact, by perfect induction or proof by exhaustion, those, for every possible combination of B, C, and D, we're going to get the same result for either the expression on the left, the expression on the right. Both of those expressions produce the same output, the same truth table. Now let's consider T9, the covering theorem. So here we have B and B or C is just equal to B. And we can see that that's true because in the AND operation, we have a B, so the only way to make that AND operation true is if B is 1. And so if B is 1, we know that already that expression, B or C, is also equal to 1. When B is 0, well, we have 0 and something. Well, it doesn't even matter if C is true because we already have a 0 in B. We get 0 and something. That's going to evaluate to 0. We also had T9 prime, the dual version of this theorem. Then we would get B or B and C is equal to B. So logically, again, this expression is going to be true. You have a bat or a bat and a cat. Well, if you have a bat, it's already true. So if B is 1, that term is true. So we get 1 or something is going to be equal to 1. In the 0 case, this first term, B, is 0. And there's no way to make that second term true, B and C, because we already have or 0 and something. So it's definitely going to be 0. So this was the case when B was equal to 1. This is the case when B is equal to 0. And this makes sense, right? That expression. You can come to the party if you have a bat or a bat and a cat. You come to the party, you have your bat in hand. Come on into the party. Come to the party, you have a cat in hand, no bat. Sorry, not coming to the party. come to the party, you have a bat and a cat. Well, great, you're definitely in, but the bat would have been just fine too. So the cat, don't really even need it. All you need to make sure is that you have that bat and you're able to come to the party. This first term, the B term, already covered the second term, the second case. So again, we can prove that this theorem is true, that the covering theorem is true by either of the two methods, perfect induction, proof by exhaustion, or the second method, using other theorems and axioms. So let's show both ways. Here's the first method, proof by perfect induction. Again, we also call this proof by exhaustion. To show all the possible cases and show that it's true for each possible case. So we have B or C. Well, the or of those two columns, we get 0, 1, 1, 1. And then we and B and B or C. And we get 0, 0. Well, these two rows are 0 and B, so 0 and something will definitely be 0. And then for the bottom, two rows, we get 1 and something. Well, that'll be just that something, so we get 1, 1. And we can see that, in fact, this left side of the equation, B and quantity B or C, is in fact equal to the right side of that equation, B. And here we have it typed out, what we just did by hand on the prior slide, and show that, in fact, those two columns are equal for every possible case of B and C. Now we can also use the second method to prove that the covering theorem or any theorem is true. So we want to use other axioms and theorems to show that each side is equivalent. So in this case, we're going to take this left-hand side and use other Boolean axioms and theorems to show that it's the same as the right-hand side. So we'll start with our original expression, B and quantity B or C. And we can use distributivity. So T8, distributivity. And we can say, okay, I'm going to distribute that B across that and. We'll get B and B. Or, there's our or, B and C. Now we can see B and B. Well, we had that theorem, idempotency, that said I can and, B and B, that's the same as just B, or I could, and it 10 times, B and B and B and B. That still is equivalent to just B. So we'll use the idempotency theorem, and we'll get, well, that B and B term just turns into B, and we also don't forget to bring down our other terms. Okay, so now we can use distributivity in the other direction and factor out this B term. So we can take B here, and just like in multiplication, that same property, B and 1 gives us this term there, or C. So I factored out the B using distributivity, again in the other direction. And now we're going to take this term, 1 or C. Well, if there's a 1 in an or expression, that nulls out the effect of any other term in that or expression. 1 or anything, in this case C, well, it's just 1, because there's a 1 in the or expression. So that term turns into 1 because of the null element theorem. So we get 1, and then we don't forget to bring down our other term. We get B and 1. And now we can use the identity theorem, where we have some term and 1, well, we're just going to get back that same term, in this case, b. So we're going to use identity here. To get equals just b. So again, here written nicely, same steps that we just did, where we showed that, in fact, we can start with this left-hand term, and using other axioms and theorems, we can make it look exactly like the right-hand term and show that those two expressions are equivalent. Okay, so let's look at the combining theorem. We can do this same thing that we did before. We can use axioms and theorems to show that this left-hand side can be manipulated to look exactly like the right-hand side. And how do we manipulate them? Well, using other axioms and theorems. Okay, so let's start with that left-hand side again. B and C, or B and C bar. And so one thing we can do is we can use distributivity to factor out that B, and we get C or C bar. So we're going to use distributivity here. And now we can see, oh, well, that term here, C or C bar, that's just complements, right? One of those terms is going to be true. So if C is true, well, that term's true, or 1. And that or expression evaluates to 1. If C is 0, well, C bar is 1. And that or expression still evaluates to 1. So no matter what C is, either 0 or 1, that expression, C or C bar, is going to evaluate to 1. And we get B and 1. Again, using T5, and specifically T5 prime if you want to put that, but T5, if you just put T5, that's okay too. Complements. And now we see the identity theorem. Anything anded with 1 will just give us back anything. So in this case, B and 1 is just B. That's the identity theorem. And we indeed showed that this left-hand side of the expression, B and C or B and C bar, is in fact equal to the right-hand side of the equation, just B. So we just showed that we can in fact use that second method, proving that it's true using other axioms and theorems. And we just proved that the combining theorem is in fact true. We could have used the first method, proof by perfect induction, as well, and we would have gotten the same result. And here it is again, what we just did on that prior page, typed out for your convenience. Okay, so let's go ahead and look at the consensus theorem, T11, and prove that this is true using both methods. So by perfect induction, and we'll also show that it's true using other axioms and theorems. So here's our consensus theorem. We'll show that it's true using perfect induction. So we have 3 terms, B, C, and D. And again, we'll write the truth table for those terms because we have 3 variables. We're going to have 2 to the 3 rows, or 8 rows. And again, these rows go in counting order, in this case from 0 to 7. And to keep alignment, I always draw a line between every 4 rows. Okay, so let's start with this first term, B and C, and then we'll do the next term, B bar and D, and the third term, C and D. So B and C, we're going to get 0, 0, 0, 0. Well, B is 0 in all of those top 4 rows. B and C, well, B is 1 in the bottom 4 rows, so we're just going to get 1 and C. So we'll just get C. 0, 0, 1, 1. Or you could do it one by one. 1 and 0, 1 and 0, 1 and 1, 1 and 1. Now we're going to get B bar D. this column here. So inverse of B is 1. So we're going to get 1 and D for those top 4 rows. So we'll just get the D column, 0, 1, 0, 1. B bar, the inverse of B is 0 in those bottom 4 rows. 1 bar is 0. So we'll just get 0 and something. Well, 0 and anything is just 0. The null element theorem. Okay, and our final column here, C and D. Well, we'll get these 2 columns ANDed together. And now we're going to OR these terms together. We'll get B and C, or B bar D, or C and D to get this expression. We're going to OR these columns together. And we'll get, so anytime there's a 1 in any of the columns, we'll get a 1, 0, 1, 0, 1, 0, 0, 1, 1. And now we can take the second expression here, B and C, or B bar D, and see what we get. B and C, or B bar D. So we're now just ORing those 2 columns together. We're going to get 0, 1, 0, 1, 0, 0, 1, 1. And in fact, we show that these 2 expressions are in fact equivalent. So we can reduce this top term, the first term, to just the bottom term. This consensus term, C and D, didn't give us any more information than we just had in the first 2 terms, B and C, or B bar D. We can also use other axioms and theorems, that second method, for showing that the consensus theorem is true. So let's start with our expression on the left, B and C, or B bar D, or C and D. So here's our expression on the left. And we want to make it look like that expression on the right of that equal sign, B and C, or B bar D. Okay, so we know that somehow we're going to get rid of that term. One thing we can do is we can say, well, I'm going to expand that using combining, or kind of reverse combining, where I can say, well, C and D, some term A, I can use reverse combining and turn that into A and B, or A and B bar. In the past, we've kind of gone the other direction, where we start with A and B, or A and B bar, and turn that into just A. But I can go in this direction too. And just like in regular algebra, that A could be some other term, in this case C and D. So C and D, that's equal to B and C and D, or B bar and C and D. So again, this is using combining in the other direction, the direction where we haven't used up until this point. So I'm expanding this term using combining. Okay, so I replace this term C and D with B, C, D, or B bar, C, D. And then I don't forget to bring down the other terms, B bar D, or BC. And you can see how I try to keep these aligned so it's easy for me to tell that I haven't forgotten to bring down one of the terms. Okay, so now we look at this and say, well, our 2 go-to theorems are covering and combining. So I see if I can do anything with covering or combining. In this case, I see, oh, this term here, B and C, and this term, well, this first term, B and C, already covered the case, or B and C and D, right? You can go to the party, if you have a bat and a cat, or, so that's this first term, a bat and a cat, or a bat and a cat and a dog. Well, guess what? Just bring the bat and the cat. You don't need the dog. That case was already covered by this case, the B and C case. Likewise, we can see that this term, B bar D, covers this term. So B bar D, you can come to the party if you don't have a bat and you have a dog, or, so that's this term, or if you don't have a bat and you have a dog and you have a cat. Leave the cat at home. Just don't bring your bat. Bring your dog with you. Okay, so we could also use commutativity to bring those terms together first, B and C. So across an or relationship, we can use commutativity to move these terms around, and associativity to move those parentheses around. And we can move B and C, or B and C and D. So we're using commutativity and associativity, or B bar D, or B bar CD. Now let's look at the last theorem, DeMorgan's theorem. And this theorem, because it's unique in that it uses these bars over an entire term, basically distributing the bars across each individual term and changing the operation. In this one, we can only use perfect induction to prove that it is true. So let's look at the case A and B, an and term that's inverted, is the same as each of those terms inverted and or together. Again, that and operation that's under an inversion turns into an or, and each of the terms gets inverted. So again, we start with our truth table. We have two terms, A and B. So we're going to have 4 rows in our truth table, 0, 0, 0, 1. 1, 0, 1, 1 shows all possibilities of A and B, so all possible combinations of A and B. And let's start with just A and B. We'll get 0, 0, 0, 1. And the inversion of that. So here's our NAND operation. 1, 1, 1, 0. I want to show that's the same as A bar or B bar. Well, we can put A bar here, B bar to those terms. So A bar is 1, 1, 0, 0. B bar is 1, 0, 1, 0. A bar or B bar, that expression, is 1, 1, 1, 0. I'm orienting these two columns together. And in fact, we can see that for every possible value or possible combination of A and B quantity bar is the same as A bar or B bar. And we could use the same method to show that the dual version of DeMorgan's theorem is true. So to recap, in this module, Module 7, we've shown that we can prove that Boolean theorems are true or valid by using either perfect induction or by using other Boolean theorems and axioms to simplify the expressions and manipulate them to show that the left side is in fact equal to the right side.